Hi, this is Nick Pizzi. This is another video in the series of hydraulics that we're doing for distribution and plant operators. This one is part 2 of the pumping and horsepower problem. So let me share that screen with you and we'll go from there. Okay, so pumping and horsepower, series of license exam training modules on hydraulics for distribution and plant operators. We mentioned before in all of our hydraulic series that in water plants and in distribution systems, we have to do hydraulic principles that require us to know some math. We use that math for determining things like detention times and pressure and head on pumps and elevated tanks. We use the math to determine velocities and flow rates as water is moving through our distribution system. And of course, we do math to determine the amount of energy needed to move that water, the horsepower that moves that water through our system. All those calculations may be necessary to do further calculations, such as ones we do for dosage and feed rates, etc. So math for hydraulics is very important. It's the basis of a lot of what we do in the water system. If we review pumping and horsepower part 1 video, and I will show you a link at the end of this presentation that will bring you back to that if you haven't seen it already. But in that part 1 video, we covered terminology. We covered the concepts of pressure and head, flow rates, and the theoretical amount of work or horsepower that it took to generate those in order to move water through our systems. We found certain things out. For example, we found that water weighs 8.34 pounds per gallon, and so it takes work to move that much weight of water somewhere. The number of gallons we have times 8.34 is going to tell us the pounds of water we have to move. We found that there's a relationship between pressure and elevation for the water we move and store. Every 2.31 feet of water elevation that we have, we're going to have 1 pound per square inch pressure at the base of that container. Now, we should realize that once we move that water up in the air, once we do the work to do that, we haven't lost that energy. We've stored it up in that reservoir. And that's a nice thing about pumping. We can pump when we want to, store it in that reservoir, and draw it back out when we want to. But that work that we do to move it up into that reservoir is called horsepower. That's the energy spent to move, on average, about 33,000 pounds of water through a distance of 1 foot in 1 minute. That work, that 33,000 foot-pounds per minute, or 550 foot-pounds per second, if you divide by 60, is equal to the amount of 746 watts, that energy, or 0.746 kilowatts. So those are some of the things we learned in part 1 video. One of the most important formulas we used to learn in part 1 video was the horsepower calculation formula. We learned that because of the relationship there exists between the amount of work needed to be done to move water to higher elevations and the amount of time it takes to do it and the elevation that we're going to move it against, the equation becomes horsepower equals the gallons per minute, in other words, the weight of the water in gallons, times the head in feet, that's the head pressure, divided by the 3960, which we knew was the 33,000 foot-pounds per second, divided by the weight of water, 8.34 pounds. That gave us 3960. Let's go from the theoretical formula above, which we knew was just in theory, to the actual world, the practical world of waterworks hydraulics, where we got to figure out that this formula has its limitations, and we need to further dress it up a bit so we can use it properly. We have to understand that in reality, pumps are machines that are not perfect. They're not 100% efficient. We also need to deal with the concept of friction losses in piping systems. The fact that some energy is lost as water works its way through our pipes. The faster it moves, the more energy we lose. We're going to cover friction losses in the part 3 video, so stay tuned for that one. That's going to come up after this. We need to calculate the actual amount of work that must be done to overcome these additional loads put on our ability to get water where it needs to go, with as much volume and pressure that our customers need. So let's review some of that terminology so we can do the formulas. So here's pumping terms and horsepower. Horsepower terminology, which are terms used to describe the types of work being done by the various components of a piping system. So there's horsepower, or HP, that's the amount of work being done. And there are 3 terms we use when we describe the horsepower. We're going to note that these are in decreasing value, decreasing size. The first is the motor horsepower, or MHP. It's the horsepower supplied to the motor in the form of electrical current. We move from there downwards to brake horsepower, or BHP. It's the horsepower supplied to the pump from the motor. Sometimes they use the word bullhead there too, bull horsepower. And then the last one is water horsepower, or WHP, which is the actual horsepower available to pump the water. So we started out big with motor horsepower. We lost some energy through inefficiencies. We went to brake horsepower. We lost more inefficiencies or more efficiency, and we brought down to water horsepower. Let's take another look at it this way. When you're moving water down, when you're moving downwards across from motor horsepower to brake horsepower to water horsepower, you always multiply by the efficiency when you do your calculations. We'll get to that. If you're going upwards, though, moving from water horsepower backwards from water horsepower up to brake horsepower, for example, you have to divide by the efficiency. So here's pump system efficiency, the terms for that. An electrical pumping system consists of a pump itself and the motor that drives it. Now, I know there are other kind of pumping systems like a gasoline engine or natural gas, that kind of thing, but we're talking about electrical systems today, making it simple. Each of these experiences some loss of power as they operate. So the motor experiences some loss of power, so it's not 100% efficient. And the pump experiences loss of power. It's not 100% efficient. Of course, these losses are due to friction, slippage, heat transfer, all that kind of thing. Each efficiency is expressed as a percent. It's always going to be less than 100% because it's not theoretical anymore. It's used in the calculations as a decimal. So example, you would use 0.85 for the efficiency of 85%. When you multiply the pump efficiency and the motor efficiency together, they'll sometimes refer to that as wire to water efficiency. So it becomes one number. For example, the motor efficiency is 85%, and if the pump efficiency is 92%, the wire to water efficiency would be the 0.85 times 0.92 or 0.782, 78.2%. So that's wire to water efficiency. So if I gave you the wire to water efficiency and the motor efficiency, you could use those numbers to get the pump efficiency and vice versa. So think about those terms also. Here's a graphic that explains water horsepower, brake horsepower, and motor horsepower. We're going to move from right to left. We're going to start out with a big arrow here pointing to the left. We're going to call that our motor horsepower, being electrical energy being fed into that motor. Now, horsepower is lost here because the conversion of electrical energy to mechanical energy is inefficient. And there's other inefficiencies in the motor. If you touch that motor while it's operating, you're going to feel it's warm. That's the proof of existence of lost efficiencies or lost power. So then the energy coming out compared to the energy we are coming in, still going in the same direction, but you notice it's smaller now. We've lost some of that energy. I'm exaggerating these sizes a bit. But you notice we've lost some energy going through that. So now we got to go to the pump. We're going to call that brake horsepower coming into the pump. And that pump has some inefficiencies also. We're going to lose here due to slippage, friction of the shaft, and other pump inefficiencies. But coming out of there is another green arrow that's even smaller. We're calling it the water horsepower. So you see where we started out with large amounts of energy being supplied to the system by way of electrical energy. When it came out of the motor, it got smaller and fed to the pump. When it came out of the pump, it got even smaller still. There's still energy left, but it's a percentage of what was originally put into the system because of those two inefficiencies. For example, if I had a 12 horsepower system that I was supplying that motor with, what is the brake horsepower and water horsepower if the motor was 90% efficient and the pump was 85% efficient? So what they're saying is, on the right-hand side, I'm coming in with 12 horsepower fed to that motor, but it's only 90% efficient, and then I'm come out of there and go to the pump, which is only 85%. What am I going to have left after those two efficiencies? Well, that's very simple. Take that 12 horsepower, take 95% of it, and then 85% of the other. I'm going to come up with what's left of a total of 9.2 water horsepower. So I went from brake horsepower coming in to the brake horsepower of 12 horsepower. 90% of that left me with 10.8 going into the pump, which was inefficient, left me with 9.2 going in to actually be available to pump the water. So I had to invest 12 horsepower to get 9.2 horsepower work going into my water. So those are the two inefficiencies described there. Let's look at some other pumping terms here for head. Head terminology, these are terms used to describe pump head locations and whether or not the pump is operating. So we have two terms called suction head and discharge head. These are head terms that describe which side of the pump you are discussing. So if I'm on the suction side of the pump, the water is coming in. That water is available to the pump. That's suction head. It's either high or low. Coming out of the pump is now discharge head. So you're on suction side or discharge side of the head. So the static head then are measurements taken on either side of the pump when the pump is not operating. Static, not operating. You add them together, you're going to get the total static head. So if you had the suction head and the discharge head together on a static system, you'll get total static head. When that pump starts operating, now we have to talk in terms of total dynamic head. This is the total head being developed when the pump operates. It's the sum of the static heads plus the friction head and inefficiencies of the pump that you must overcome. So here's some pictures that'll help us understand that. This is a diagram of a pump with static suction head. Notice the pump down at the bottom middle. Pump is not operating. There's two heads being developed, being shown here. One is the static head on the suction side, static suction head, where the reservoir of water is sitting higher than the pump. So that's pressure in terms of head available to the pump. Now the pump wants to move that water up to the other elevation there. It has done so and has now been shut off. You notice that it's a higher elevation on the right. So the difference between the two becomes the total static head, the higher elevation minus the lower elevation. So in other words, if that pump were doing that work to move that water, it does not have to do the work that the static suction head supplied to it because it's higher than the pump. So that I don't have to overcome that. If I were to turn that system on, the only head I have to overcome in this theoretical system is from one elevation of the tank to the other, because that's a static suction head. Now that's different than a static suction lift. Here on the suction side of the pump, we notice that water is at a lower level than the pump, lower than the center line of the pump. I'll go back to the last slide. Then the higher, it's on higher than the pump. Here it's lower than the pump. Now the pump, if it were to come on, has to pull that water up. It has to draw that water out of that reservoir up through that elevation before it can then start pushing water up into the other tank. So now the total static head becomes the height above the center line plus the different distance below the center line. We add those two together. They're going to be different than the other situation. Now those are the two situations when the pump is not running. Suction lift, suction head. Now there's total dynamic head, pump operating with a head loss. You see the pump is there in the middle lower section of the graphic. It's operating. I've got a suction head, not a suction lift. The total static head is going to be the difference between the two heads as described before, plus additional head is required to compensate for friction and minor head losses. So this is a dynamic head that's pumping. Another way to look at it is that section in the middle top of the slide there that shows you just a short distance where the additional head required to compensate for friction and minor head losses. If there were no friction in this system, which we know there always is when you're pumping water and through a distribution system, if there were no friction, that tank level on the right-hand side would be actually that much higher because I didn't have to overcome that. But because I'm pumping against those friction losses, I'm only able to get the water up that high that you see in the tank, a little bit lower than what would have been if I didn't have friction losses. That's how you think about total dynamic head in a working system with head loss. Now, just briefly as a teaser for the next video we're going to do, part 3 of this series, I'm going to talk a little bit about pump curve terminology. I'm going to talk a little bit about it on a light level, and then we'll get into some heavier stuff on the next presentation, I promise. We're going to look at a quick pump curve, a simple one, where we got 3 curves. We got the head curve, or HQ, shows the relationship between the total head against which the pump is operating and the pump capacity. We're going to look at the PQ line, which is the power curve. It shows the relationship between power and capacity. And the EQ line, that's your efficiency curve. That's one we're very much interested in here. Shows the relationship between pump efficiency and the capacity. And we'll see from the graph, when we're pumping at various flow rates, how efficient we become. And in general, when you get a pumping system, you're going to find there's a spot right in the middle of the line where we want to be the most efficient, or we can be the most efficient. We vary from either side on pumpage capacity. We become less efficient in what we're doing. The whole idea is to try to run the pump in the efficiency curve as best you can. Here's what it looks like. Here's the pump curve on the left, and you notice the graphic is labeled on the left y-axis as total head in feet, and on the right y-axis going up and down is the brake horsepower and also the percent pump efficiency. On the bottom x-axis, going from 0 to 22, is the capacity Q in 100 gallon per minute units. So in other words, the way to read that is if I were to locate 4 on the bottom of that chart there, 4 times 100 would be 400 gallon per minute. So this goes from 0 to 2200 gallon per minute. We can see immediately that efficiency curve that goes up as a loop upwards and then breaks back down again. So it's like a roller coaster going up and down. If I were to find the high point of that EQ curve, the best point of efficiency on that curve, find that spot on that curve and take that line straight down, I would see that at 14, in other words, 1,400 gallons per minute, this pump is most efficient. This pumping system, I should say, is most efficient. On either side of that line, at 1,200 gallons per minute or 1,600 gallons per minute, I'm not as efficient. So if this pump doesn't put out 1,400 gallons per minute, there's more wasted energy. There's more inefficiencies, and that would play into your horsepower equation. And we'll do that on the next presentation that we do. You can also follow the PQ curve and HQ curve and play with those lines and see exactly what they mean. So in other words, at that same pumpage of 1,400 gallons per minute, when I was most efficient, I could follow that EQ line, the top of the EQ line, that point right there, and break it down and straight down to the HQ line and find that the total head and feet would be about 140 PSI. In other words, when this pump, I'm sorry, 140 feet, not PSI. So when this pump is putting out 1,400 gallons per minute and is most efficient, it's putting out about 100, it's working at about 140 foot head. And you can convert that to horsepower or to pressure if you wanted to. You'd also find out if you continue to go down, you're going to hit the PQ line. You're going to hit the pump headline, the pump pressure line, and see the brake horsepower and all that. So you can just follow that curve at any efficiency and figure out where you're pumping and what your efficiencies and hit are. So that's the power curve, the PQ line, all right? So again, we're about finished. I will point out to you that at the end of all of our hydraulics series, we've got these charts that we can put up that you can use to work on some of your problems. And I would remind you, I'm going to stop sharing this chart, and remind you that this series is ongoing. We'll be adding to it. You'll see a button come up on your left-hand side, a button come up on your right-hand side. If you want to see more of these videos, you click on the right-hand button. If you want to subscribe, you click on the left-hand button, and you'll get notices when we put more of these on. So I hope this was useful to you. Look back in a few days, and we'll have another one ready to go. Thanks.